Thank you. Thank you very much. And I would like to also thank the organizers of this nice workshop. I didn't understand almost anything, which is, I think, the part of the job, because the purpose of the workshops is to get know with the things which you don't know. So in this case, it was, from this point of view, it was amazing. Thank you very much. I'm here because I'm representing a small international groups of scientists interested in the data-driven modeling, especially Ilya Horenko, Professor Ilya Horenko from Lugano, from Switzerland. I used to work for him as a postdoc for the last 4 years, but now I'm working somewhere else. Actually, he's an author of most of the ideas which I'm going to present you today. We are also cooperating with Professor Susanne Gerber from Mainz in Germany. She is supporting us not only with the problems from bioinformatics, and then me, I'm interested mostly in the optimization, in the developing of the optimization algorithms for solving big data problems. I'm interested also in the implementation, HPC implementation, mostly on multi-GPU things, architectures. But as you can see, I'm not the right person from our group which should present this topic to you. Anyway, but Ilya said that this topic is so simple that even I will be able to talk about it. So there are also other peoples which I like, so I decided to put them on the slide. Yeah, I would like to talk about two topics. The first idea is older. It's about non-stationary time series analysis based on the clustering, based on the separation of the data into the smaller regimes, and then applying much more simple models to these regimes. And this approach decreases the complexity of overall model, which is applied to fit the data. These methods are called FEM-H1 and FEM-BV. We made a lot of progress with them. And the second topic is much more interesting. It's completely new. We finished the paper last year, and we are in the final stage of the publishing it. So I hope it will be published very soon. It's about scalable probabilistic approximation. It's the method for reducing the data, but the interesting is that this method scales linearly with the size of the data. In my opinion, it's very interesting, because if you try to write down the list of the algorithms which are able to reduce the data in such a way that the computational complexity will grow linearly with the size of the data, then your list will be very short. Actually, only k-means based algorithms are able to do that, in my opinion. So, the first topic. So let's say that this is the time series, the data measured in the time, one-dimensional. So what we can do with it? I mean, usually in the case of the modeling, we are trying to understand what is inside the black box, which has generated this data. However, there is also some noise, and so on. So what typically we are assuming that there exists some model function which describes the process of the generating of this data plus some noise. And then we choose some model, and we try to fit this model to the data to find the optimal parameters such that this model fits the data in the best way. For example, linear regression. Yeah, this curve has two optimal parameters, so actually we are solving the optimization problem. We are trying to find these two coefficients such that this norm is minimal, quite simple. Yeah, why I'm talking about it? Yeah, because in other cases, we have to choose more sophisticated models. If we stick with polynomial regression, then to fit, for example, this data, we can increase the degree of our polynomial function to, let's say, 49. We have 50 points. So if we choose the polynomial, the degree of our polynomial fit function to 49, then actually we are not approximating, we are interpolating, so the model error is 0. So this is the best model. Actually, this is not the truth. Yeah, we have lower modeling error. However, we didn't reduce the noise because we capture also this noise in our model. This is something which is called overfitting, and also there is a little problem with the interpretation of the results, because when we are talking about so complex model, then it's quite hard to say which parameter of this model means what. Yeah, and there are also other things. Something like the complexity. If we have more parameters which we have to estimate, then we have the larger optimization problem. We have more unknowns. For example, in the case of polynomial regression, we obtain here the matrix, which is invertible. It can be proven theoretically that it's always invertible. However, from the computational point of view, the condition number grows exponentially with the degree of the polynomial function which we are using to model the data. Yeah. So we have two things which we would like to minimize. We would like to minimize the modeling error, but in the same time, we would like to have as simple model as possible. So we would like to follow something which is called Occam's razor principle. Yeah, so we would like to find the simple model which fits the data the best. For example, if you apply this theory to check if the Moore's law is fulfilled, then you will see that not anymore. Actually, we are right now on the plateau, so the computational resources are not growing exponentially anymore. Yeah, but it's... Yeah, but let's talk about something more optimistic. So suppose that we have signal like this. We are switching between two processes, between two states, and we have some noise in the data. Yeah, we have some true signal, we add some noise. In this case, it's a Gaussian noise, and we would like to apply some standard methods like moving Gaussian window, which will reconstruct the data in this way. Or we can try to apply Gaussian hidden Markov models, and we will get these results. So this is working. The problem is that when we increase the noise of the data, which is a typical situation in, for example, neurosciences, like EEG signals and so on, where the signal to noise ratio is really low, then these standard methods are not working anymore. Recently, we published a paper where we are solving something similar. We are solving the problem of switching. We have a signal which is switching between two states. Here is a zoom of this smaller window. Here you can see that we was able to reconstruct the signal almost precisely. This is only the first part of the signal. The overall size of the signal is around 10 millions. We solve it on a PIS-9 supercomputer on GPUs, and I think that we are quite good. And we also compared our method to other standard methods, and it seems that our filtering error is the best. So I would like to talk about the way how we did it. It's based on the regimes. So this is our approach. We suppose that in our signal there are some regimes where the parameters are not changing. So at first we split the data to the regimes, and then we will apply locally to these regimes our simple model. So in this case we suppose that our model is a constant, and we are solving this problem. So it's a constant regression, amazing, constant regression, but in a particular, in the given k-means, we are applying only the parameter which corresponds to this regime. Yeah, but the question is how to split the time series into the regimes. I mean, if you have right splitting, then it's quite simple. Yeah. So instead of this sum, which is only through the given regime, we can introduce something which is called regime indicator function. This will be the function which is equal to 1 if given T is from given kth cluster, and it's equal to 0 for all other clusters. So actually what we are trying to solve is this optimization problem where gamma is binary, and there is also additional constraint that only one cluster is active in each time step, and also another set of the parameters are the parameters of the local models on the regimes. So we are trying to solve both of the clustering problem, both of the finding regime problems and the local modeling in one optimization problem. And this thing is not new. Actually, this is the same problem which you can find in K-means algorithm. Yesterday you said that you know the K-means algorithm, so I will make a very short review. So K-means algorithm is a question.
Yeah, the previous slide, but gamma K, I mean, do you know it or?
No, it's an unknown. So this is quite funny because we mix two things together. We don't know the regimes, and in the same time we don't know the parameters on these regimes. Yeah, and it's quite funny that this objective function is actually the same objective function which is in the K-means. So that's the reason why I'm talking about it. So it's unsupervised learning algorithm. We don't know the centroids of the clusters, and we don't know the affiliation. Yeah, and we suppose that the cluster consists only of the similar problem points and blah 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 blah. That's quite clear. And each cluster can be characterized by the mean value, which is called centroid. Yes. So actually, we are solving the same problem. In this case, the affiliation to the given cluster is described by the cluster indicator function, which in the case of non-stationary modeling, it's a regime indicator function, and still there is a condition that only one regime is active in every time step. And how the K-means works? Actually, it splits the problem into two problems. At first, we solve the problem in one variable, and then in the remaining variable. It's a subspace algorithm. So, for example, if you want to solve this problem in gamma with the given centroids, then what you are actually doing, it can be shown that this problem has analytical solution, and actually you set the corresponding component of gamma to 1, corresponding to the closest cluster. And on the other hand, when you are trying to solve the problem of the centroids, then actually you are computing the mean value only of the points which belongs to this cluster. And again, it can be written in terms of the gamma and x. So we can formulate the K-means problem as the same optimization problem as in our case. So we can solve it. We can solve the problem. Yeah, this blue line, which you cannot see, is the signal, and the red line is the origin signal without the noise. So we can see that our process is able to, here is a gamma, which you cannot see. You can see that our algorithm is able to find the right regimes. If you increase the noise, then the situation is quite different and a little bit worse. And if you increase the noise even more, then it stopped to work. What is the problem? The problem is that the K-means ignores or doesn't take into the account the time. I mean, it was developed to classify some general points, not the time series. So if you take a look into the objective function, then you can make a permutation of the points in time, and still the objective function will be the same. So there is an assumption we would like to say that our regimes are somehow persistent in the time. So the regimes are not switching in the crazy way, because usually the switching of the original signal is caused by the noise, but our gamma should not switch as much as our signal. How to do that? We can use a regularization. In this case, we are using H1 norm as an additional term to our objective function. So there will be a parameter epsilon which will say which of these two optimization problems, which of these two parts of the objective function is more important. I mean, if epsilon is equal to 0, then we are solving the original problem. If epsilon is large, then what we are trying to do, we are trying to find such a gamma that this term is as low as possible. Here you can see some examples. If you have some crazy noisy data, noisy gamma, then the norm is large. If you have smooth functions, then the norm is small. If you have a constant gamma, then the norm is equal to 0, because actually this is the Euclidean norm of the derivative. Yeah, exactly. Another assumption, we don't want to solve the binary optimization problem, so we will relax our affiliation. So we take the continuous gamma from 0 to 1, and still we will assume that when we sum these gammas in each time step, then we will obtain 1. Actually, in this case, these gammas can be considered to be a probabilities of belonging the point to the regime. So we will not make hard clustering like 0 and 1, but now we will consider the probabilities of belonging to the given cluster. And on the other hand, a solution of the continuous problem is much more easier than the solution of the binary problem. Yes, and still we are using the same algorithm. In this case, the gamma, the centroids, the problem is still the same, because this new term didn't affect the solution in theta. But in the case of the gamma, we don't have analytic solution anymore, and we have to solve the quadratic programming problem, because this term can be written as a gamma transposed times h times gamma, where h is a Laplace matrix which corresponds to the graph, to the path. And this linear term, full of errors, can be written right here. So we have to solve this convex quadratic programming problem. H is symmetric positive semi-definite because the kernel is a vector full of ones. And we have also some constraints saying that gamma has to be from 0 to 1, and the sum is equal to 1. So we have linear equality constraints and lower bounds, because actually this constraint, this upper bound, can be ignored, and still the feasible sets are equivalent, which is quite interesting. We tried to solve this problem using quadproc in the MATLAB, and it didn't work. So then I came to the group, and I am an expert in quadratic programming. So I modified the Spectral Projected Gradient method, which has been proposed by Professor Martinez and his group. I modified it to solve the quadratic programming problems more efficiently, because I observed that additional line search is a projected gradient method. So at first you try to use the standard gradient descent method, where the step size is computed as a Barzilai-Borvan step, which approximates the inverse of the spectrum of the Hessian matrix and so on. Wrong community. Yeah, I know. Yeah. So it's working, and it's nice, and it's amazing. And it's based on the projections. I have to project the point onto the feasible set, which in this case, if you have these constraints, like the sum of the gamma equal to 1, and the bound constraints, that actually our feasible set is composed from the separable simplexes. So this is an example when the number of clusters is equal to 3, the feasible set is actually the simplex. And the projection onto the simplex is known. I mean, there exists a finite algorithm to find this projection.
So what's the complexity of each iteration?
Good question. We have to multiply with the sparse Hessian matrix, with the triagonal matrix, which is OTK. That's the most expensive operation. T is the length of the time series, and K is the number of clusters.
Okay.
Yeah, but because it's a triagonal matrix, then the complexity is T times K, which is awesome, in my opinion.
It's a linear complexity.
Yep, it has linear complexity. Question?
Yeah, just a simple question. So here, like, you always assume that capital K is none, or?
That's a good question. Typically, we solve the problem for several values of K, and then using the standard procedures, we decide which K is the best one. Like AIC, BIC, and information criteria. Me neither. Before I came to the group of Ilya. Yeah, so here is how it works. If on this slide, I just want to say that if you choose large epsilon, then you will obtain smoother function, gamma. If you use small epsilon, then yeah, it's not so smooth. I mean, it's quite clear. I was talking about. The question is how to choose the epsilon for given K. How to find the right epsilon, because I have generated the auxiliary data. We can compute the reconstruction error, and we can see that for small epsilon, we have some crazy signal. For large epsilon, too large epsilon, we have a constant function, and the right epsilon is somewhere between these two values. But this curve can be constructed only if we know the exact solution. But if we know the exact solution, then there is a question why we should solve the problem in the first place. Yeah, it doesn't make any sense. So we are using something which is called L curve, which is a construction of this curve for several values of epsilon. We solve the problem, and then we choose the right point somewhere in the edge. Yeah. For example, extensions. This is working. This is nice. Possible extensions. Instead of time series, you can also consider the signal both in time and space. And then you can use also the space regularization, not only the time regularization. There is a nice paper about it. So if you have signal which is working on some particular graph, then you can impose this information about the graph into your regularization. Another possible extensions, the question is why we are using the constant model. Actually, we can use any model, any stationary model, and extend it by these non-stationary settings. This is piecewise linear regression. And here is a comparison that if you use the polynomial regression instead of this approach, then to obtain the similar reconstruction error, you need the polynomial of degree 50. But in this case, you have 3 regimes, and on each regime, you have linear function.
So, I'm just trying to think about this capital K. You have a noise, and it's all like changing all the time. How would you distinguish between the regimes of the noise and the regimes of the signal?
Regimes of the noise.
Because the noise is like changing all the time. So how would you know?
We have never tried to capture the noise. I mean, we suppose that the noise is IID through all the signal.
There's the method, I mean, clearly distinguishes between the signal and the noise or something.
Yeah, so you can try to apply it. Maybe it will work. Another question.
Yes, for the graph method.
Yeah.
So that method that you're using for graph is called Laplacian regularization. The penalty theorem.
Yeah. Yeah. Because in the previous case, this matrix H was actually the Laplace matrix which corresponds to the path.
Yeah, so parallelizing by least squared correct distances along edges is Laplace regularization.
You mean the additional regularization term?
Yeah, the penalty epsilon squared times the penalty, that's called Laplacian regularization.
So it already exists. It's nice. Okay, thank you. Yeah, and recently my colleague Anna wrote a PhD thesis where she extended this approach to the non-stationary entropy, and she analyzed the financial data, which is also nice. I don't know anything about it, but the paper, she wrote also a paper about it. So if you are interested, you can read it. She's able to find the regimes in the financial data based on the volatility. Yeah, that's the word which they are using. So this was about the first topic. Now I would like to talk about the second one, the new one. We call it Scalable Probabilistic Approximation, and we would like to reduce the data in the same way as k-means, but in the better way. So suppose I have some data. Now I'm not talking about the time series. I have some data x, and I would like to reduce them to some clusters, let's say, because this setting will be for k-means like thing. Yeah, I can use k-means. I will directly. Yeah, I can use k-means to do that. So I have some point x, and I can use k-means to discretize the data to reduce the number of points which I have. And in this case, in the soft settings, these gammas can represent the probabilities of xt to belong to the kth cluster. If you are using gamma from 0 to 1, and the sum in each t is equal to 1. So you can use this thing to discretize the data. Actually, no. This is not true. Because in these settings, actually what gamma means is the probability of observing error, like this. Not the probability of xt to belong to the kth cluster. If we would like to write down this thing, this probability, then it should look like this. I mean, xt should be able to represent as a sk, which are the parameters of the clusters, times the probability of xt belonging to this given cluster. So actually, this is the problem which we should solve instead of k-means. It looks like this. I mean, it's not the gamma kt times the error, but the error of xt minus the convex combination of the cluster centroids. And this is the idea. And we wrote a paper about it, and we name it Scalable Probabilistic Approximation. I mean, the name probabilistic approximation is quite clear, because we are approximating the data in the probabilistic way. Scalable, because we are still using the same algorithm as in the case of the k-means, and the complexity is linear in t, is OT. How these two things are connected? Actually, if you apply the Jensen inequality to this term, then you will obtain the k-means objective function, which means that in fact the k-means is suboptimal. So the SPA should be able to represent the data in the better way. If you suppose hard clustering, then these two things, two objective functions, are exactly the same. It can be proven very easily. So yeah, and it's scalable because we are using still the same algorithm. We fix one variable, solve the problem in the remaining one, and so on. In the paper, we formulated the problem in much more general way. We can show that if you use any reasonable distance function between the points and the probabilistic representation, and also some reasonable regularization, then this algorithm will still work. Yeah, in this case, the solution of these optimization problems are quite easy and simple. In the case of gamma, we are solving the separable quadratic programming problems. But the idea is that this problem is separable in T. So for example, if you are implementing the algorithm on a GPU, then each thread can solve each of these quadratic programming problems separately. In the case of S, there is a problem because we don't know if gamma-gamma transposed matrix is invertible. So in fact, the system of all solutions of this system of linear equations is given by this with the pseudo-inverse plus the span of the null space of this matrix. So the regularization. So we introduce the regularization on the S problem, which looks like this. And then it's quite funny that the system matrix with this regularization in the case of S is invertible. So you can solve the system of these linear equations using any favorite algorithm. And it can be also shown that this type of the regularization also works as a feature selection. So you are minimizing the distance between the components of SI in the different clusters. So actually this regularization works also as a feature selection. Why? Why should we do this? I mean, is it useful? I mean, this representation. So we can use this probabilistic representation, for example, in the case of the models based on the exact law of the total probability, because if we have the categorical signals X and Y, then we can formulate the law of the total probability. Here the matrix lambda includes all of the conditional probabilities, and here is the probability of xt be in the given state, and here we have you know the exact law of the total probability. So it looks like this, and this gamma, these probabilities of X and Y being in given state can be taken from SPA. So if I have two continuous signals, X and Y, I can apply SPA to the both of them, take gamma, and find corresponding conditional probabilities solving this problem. Especially if for example, if you choose yt equal to the next value in x in t plus 1, then actually we are talking about the Markov model. So we can apply the Markov model to the continuous signal using this algorithm. And we test it. We have some results. These are two results from the bioinformatics. Here is the breast cancer diagnosis. Here you can see that in this case, the SPA has much more better approximation error than all other algorithms which we tried, including the k-means or self-organizing maps and so on. And also the better classification error. This is another example. And here we can see that also in this example, the approximation error is much more lower, and also the classification error is much more better. And we also try to apply this simple idea to the time series. Here you cannot see results because the figures are very small. So read the paper. Please read the paper if you are interested in the results. I mean, in the paper, there are all the parameters of our simulations and so on. The idea is that the message is that SPA is much more better in terms of both of approximation and the prediction. We tested it, for example, on the Lorentz oscillator, on the prediction of the temperature, on the EEG data, which are the signals from the brain which are with a large noise, and so on. One last idea. If we have this schema, then the idea is to combine all of these optimization problems into one optimization problem. So we would like to combine the feature selection, the discretization, and also the model training, in this case, this model training, in one optimization problem. And this can be done very easily in the case of SPA. So we have the SPA problem for Y, SPA problem for X, and if we substitute instead of gamma Y, if we substitute lambda times gamma X, then we will obtain actually one SPA problem with additional hyperparameter. So that's the idea, that it's possible to combine the discretization and feature selection and the model training in one optimization problem. And this is the idea on which we are working right now. And I would like to thank you for your attention.